magnetic field is sure because of the red blood corpuscles. So iron, right? That creates when these particles are in, it creates magnetic field. That's how the magnetic MRI, magnetic resonance imaging, that is totally a new chapter. When you study magnetism in grade 12, you will learn this. Anyway, now you imagine a small body. So capital M is a massive body. You imagine, say, a car of mass M and compare with that of the mass of the Earth, right? If you compare a car and if you compare the mass of a car and the mass of your Earth, you see how much variation it has. So you think you have a body of mass M is equivalent to a car. That is how you imagine. Capital, the one which produces a gravitational field, is as massive as your Earth. So now consider this body was at infinity, say a car or any body, right, whose mass is incomparable with the mass of the Earth, was lying at infinity. You want to bring this body from infinity to point P, then you have to do a work. You have to apply a force, you have to move the body, you have to do a work. Whatever work you do in bringing this body of mass small m from infinity to point P, that work will be stored as an energy in the body, and such energy we call it as gravitational potential energy. So we need to derive an expression for it. So what is gravitational potential energy? Gravitational potential energy at a point, it's point specific. At different point, the potential is different. The gravitational potential energy at a point in a gravitational field is nothing but the work done in bringing a mass which was initially located at infinity to that point. Was copy down the statement and we'll derive an expression for it. Right, boys? Gravitational potential energy at a given point. Yes, boss.
Is this the diagram we should draw?
No, no need, boys. No.
Okay.
I will redraw this. At a given point is defined as the work done in bringing a body from infinity. So you're bringing a body from where? From infinity to the given point. So it is defined as the work done.
I'm sure it doesn't of that small body. Only on the
only condition is that the smaller body will also produce a gravitational field. That gravitational field should not affect this field. You understand?
Okay.
So the field produced by the small m should be negligible. Each one of us, every human is also producing a gravitational field, right? But the field is not prominent. The reason is that it's a very weak field.
Yes, ma'am.
Copy down the statement. I'll go for the diagram.
Ma'am.
Yes.
Ma'am, like, can you say this for the moon and the earth? Like, does the moon's gravitational field affect the earth?
Why not?
Like,
It's affecting the earth. That otherwise you will not get tides, right?
yeah,
You don't
okay.
get tides. It's affecting. It's affecting.
So then we can't use this, right?
No.
Okay, ma'am.
It is that you are not, see, earth is attracting you, but you don't attract earth. See, when you're, for that matter, any person who is falling, undergoing a free fall, say a person is jumping from the person is accelerated towards the earth. Is the earth is moving towards the person? Yes, so is your earth gravitating? No, right? The reason is
That's because the earth mass of earth is like disproportion. I mean, like disproportionately bigger than the mass of the object, right?
yeah, that is also there. Now, suppose A is equal to F upon M. See, the earth is applying a force on a person. The same amount of force the person is also going to apply Newton's third law of motion comes into picture, boys. See, when a person is applying, Earth is applying a force on a person, the person will also apply an equal amount of force. So the force acting on both the bodies are the same. Then if F is a constant, A is inversely proportional to M, which means if the mass of the object, sorry, is that correct? F is equal to M into A, correct? So if the mass of the object is greater, inversely proportional to M, what does it mean?
Ma'am, so the falling man and the earth, they both exert the same force on each other, but the acceleration of the earth is is not there.
Because of
The mass. Okay, ma'am.
that's how it was ninth grade, the beginning, ninth grade, when you start your gravitation chapter, this is what you learn, right? Okay.
Yes,
I have
ma'am,
to
yes,
go
ma'am.
further. But not this diagram, I'll go for an empty slide. How is that you're going to derive an expression? You just write heading, deriving an expression for gravitational potential energy. I'll write it as capital GPE. You understand? You understand what's gravitational potential energy? Okay.
Yes.
What we'll do is, so we are considering a body of mass M, right? Center O. I'll take two different points, P and Q. The distance between PQ is dx. The distance between P to the center of the Earth. Anyway, if I'm taking it as Earth, it's fine. Or any other body, this distance is x. Now let us consider a point A, which is at a distance of r meters from the center of the Earth. Okay, right, boys? So now I'm imagining a body. Okay, this body is creating a gravitational field. Right? The body is creating a gravitational field. I want to find what is the potential energy at point A. For that, I have to imagine a mass M is lying at infinity. Now, I have to do a work in bringing this body from infinity to this point. So whatever work I do in bringing this body from infinity, the body of the of one body to the center of the other body. So when you are considering massive bodies, it has to be to the center. So the body was initially lying at infinity. From infinity, the body has to be brought to the point A. So you need to do work. Now, whatever work you do in bringing the body from infinity to point A will be stored as an energy in the body at point A. Is that clear, boys? So what I have to consider, let me consider a very small body of mass M lying at infinity. Then how much work I have to do in bringing this body from infinity to point A, which is at a distance of r meters, say from infinity to a distance of r meters, and placing the body finally at point A. That work gives you, now you're bringing and keeping the body at point A. So now the body has some energy stored in it. Where does the energy comes from? You have done a work, and that work will be stored as an energy in the body when it is going to lie at point A. So what is that energy? What is the expression for the energy? That is what we are moving on. Is that clear, boys? 11C, so 11B.
Yes, ma'am, it's clear.
Okay, fine. Now what will,
Yes.
so for that, okay, boys, for that, what we'll consider is, we'll find the small one. This is how we move on. Initially, what we consider, let the body of mass M You can draw the diagram and you can write, boys. Let the body of mass small m is initially at point P. It is initially at point P at a distance of x meters, distance of x from the center of the earth. Sorry, from the center O. Need not be earth. Right. So I'm considering the body is at point P. So then the body will experience a force. Naturally, the body will experience a force. So the force experienced by the body at point P so which is creating a gravitational field. The massive body is creating a gravitational field. So now at point P. So the force experienced F is equal to G, because you have two different bodies here, mass small m and capital M. GMM divided by, when the body is at point P, it is at a distance of x meters from the center. So to derive this, you are just considering the body of mass m initial point P, which is at a distance of x meters from the center of the earth, from the center of the other body. So then the force of attraction between these two bodies, as per Newton's universal law of gravitation, F is equal to G m into m divided by x squared. Now what you are doing is that you are moving the body from point P to point Q, traveling a very small distance dx. So let us find what is the work done. So work done in moving the body from point P to Q. From point, yes, what happened?
Ma'am, the body should be at infinity, right? Like
No,
the
no, yeah, that is what you have to calculate, boys. That is what you have to calculate. Now, how are you going to calculate? You're going to calculate, find what is the small work you have to do from P to Q, then you can go for the larger work.
Okay, ma'am.
I think it is from infinity to point A is your, when you study, when you write your annual examination, all the portions covered. From P to Q, you think it is your PT1. That's it. Your PT1, you'll have less amount of portion. PT2, still it increases half yearly, quarterly, half yearly, finally. So you're going stepwise, same thing. So the work done in moving the body from P to Q. What is that? dW, sorry, dW is equal to F into dx. So that becomes G m divided by x squared into dx. So this is the work done in moving the body from P to Q. Okay. Then what will be the work done in moving the body from infinity to a distance of r? You have to integrate between the limits. Upper limit is, sorry, lower limit is infinity. You're bringing from infinity to a distance of r meters. It is just adding all the work done. In that sense, this entire path is divided into dx from infinity to this dx equal. So find all the work done. Mathematics, you are doing the limits, right?
We are doing probability right now. We didn't start.
Probability. Probability is an easy chapter. Have you completed, boys?
Ma'am, the work done, it will be small, right? Like small.
Because the displacement is very small.
Okay, ma'am.
infinitesimally small. The reason is your force is a variable force. So I'm not going into the depth, then you will be finding it still more confusing. So let it go as this, because at least next week I have to start. Because whenever zero period, because zero period will be there, the lower grades are writing asset practice test. So if that is the case, I'll borrow your, at least any one class next week, I'll borrow from your class teacher zero period so that I can do the numericals for you as I'm continuing with the next volume. Shall I move for the next slide?
Sure, ma'am.
What is that? Total work done in bringing the body from infinity to point A, that is to point A, that is at a distance of R. Was point, I'm just like PT. That is the distances R. So what is that? W becomes equal to dW, right? Is equal to lower limit, because it's starting from infinity, reaching R, G M by x squared into dx. We need to apply the identity. Boys, when the distance is varying from infinity to R, gravitation constant is not going to vary. The mass of the body which is creating the field is also not going to vary. The mass of the body which is coming from infinity is also not varying, but this variation, we generally neglect air resistance. Otherwise, what happens when you're bringing the body, only thing is that the body will not be accelerated. I'm not using this condition. If the body gets accelerated, if the body doesn't get accelerated, then every time the Earth will experience meteorite showers. See, meteors are reaching Earth's, it's reaching somewhere near the Earth, but it's not entering into the Earth's atmosphere, because when these meteorites somewhere reaches near the Earth, it will be accelerated. As it accelerates, the body will be, because the acceleration is what? Kinetic energy keeps on increasing. And the kinetic energy increases. Kinetic theory of gases you have learned in chemistry. Was kinetic theory of gas. So when the kinetic energy of the gaseous molecule increases, the temperature will increase. So when the temperature increases, the body will get burnt up. That is the reason the whatever from your cosmos, whatever parts might be your meteorites or asteroids, they cannot enter the Earth's atmosphere unless and until the body is massive. The reason is the moment they enter into your Earth's atmosphere, they get accelerated. When they get accelerated, their kinetic energy will increase to such an extent, the temperature reaches max. The temperature will also increase accordingly, so they get burnt up before they reach the surface of the Earth. Anyway, this body, what you're bringing from infinity, you're not accelerating. It should not be accelerated. Anyway, so as the body is being brought, its mass is not going to change. The mass of the body, which is creating the gravitational field, both the m's are going to remain a constant. Gravitation constant, g is always a constant. So I'm removing that outside the integral sign, so that in that case, it becomes gmm limit infinity to r. I have dx by x squared. So I can write this x square as g m m limit infinity to r x to the power of minus 2 dx. Correct, boss? Is that fine? Okay. Now I'll go for the identity. Identity is x to the power of n dx will be equal to x to the power of n plus 1 divided by n plus 1. Here, what is n? N is minus 2. Here n is -2 boys. So what I can do is W becomes equal to G m x to the power of -2 plus 1 divided by -2 plus 1. W is equal to G m x to the power of, but anyway, limits are there, infinity to R. X to the power of so W becomes equal to G m x to the power of -1 divided by -1. Is that clear, boys? 11b. 11b.
Yes, ma'am.
Hitesh. So G Hitesh. So in that case, you'll have x to the power of -1. The negative sign comes outside. X to the power of -1, infinity to R. So how will I write x to the power of -1? 1 by x. So W becomes equal to minus GMM into 1 by x. X to the power of -1. So infinity to R. Now I have to substitute the value of x, lower limit and upper limit. So W becomes minus GMM into x takes the lower limit, upper limit first, then it takes the lower limit. So anyway, 1 by infinity is 0. So W becomes equal to minus GM divided by capital R. Now this is the work done in bringing a body of mass small m from infinity to the point A. And this work done will be stored as a potential energy in the body. So this work done is stored as the potential energy.
Ma'am,
Yes.
so since the work done is negative, that means
The force is
energy is
attractive.
negative.
The
Okay,
force
okay.
between both the bodies is attractive. So right, boys, this work done is stored as the potential
Like work
energy.
is done by the body.
Work is done?
By the body.
Yeah, which creates a gravitational field.
Okay,
Correct.
got it, understood. Thank you.
This work done is stored as, and gravitational potential energy, we denote it with, if I'm writing the entire board becomes, I'll just put this as U. You generally represent it with U.
Ma'am, can you tell again why is it negative?
Negative is that the force between both the bodies are attractive.
Okay, ma'am.
Or else you can go this way also, in which, see, the bodies, the smaller body is moving to the larger body. There is a force of attraction. And when the body is, the smaller one is reaching the larger one, the effort you have to put becomes lesser.
Okay, ma'am.
It becomes lesser because there is a strong pull. See, in what way you can say, when you're moving in the direction of the flow of water, it's easy for you to flow. So it's easy for you to swim. In case if you're swimming in the direction of the water flow, it's easy to swim. But you swim in a direction opposite to the direction of the flow of water. Is it easy?
No, ma'am.
It's difficult. That's the thing. So when you're bringing the body from infinity towards the body which is creating the field, already there is a force of attraction. Your effort as you're bringing the body closer and closer to the body which is creating the field, it will be easier for you. The reason is the heavier one is pulling it. So your effort will become less. Your effort is less means what? Your work is becoming less. So the energy also becomes lesser and lesser. That is why I have a negative sign. Or in other words, whenever the force between both the bodies are attractive, the force is negative. So work done will also be negative. You can argue in both the ways. Have you completed this, boys? Then we'll see potential. Harish?
Yes, ma'am.
Okay. There. I need to call someone. Dheeraj? Derek?
Yes, ma'am.
Okay. Nabil?
Oh, yes, ma'am.
I'm just randomly calling. Have you
Okay.
completed? I'll finish. I'll just only one topic left. I'll finish this voice.
Sure.
Shall I move for the next one, boys?
Yes,
If
ma'am.
someone just take the screenshot and just
Sure, ma'am. I'll
put
do
it
it.
in. Next, the last topic is gravitational potential. Okay, fine. One more thing. Geostationary satellites we do have. So I want someone to take up geostationary satellite as PowerPoint presentation. Two of you can share. I don't want to tax Siddharth or someone often. It has to be, otherwise I will assign the work.
Sorry, ma'am, what? I got disconnected.
Geostationary, because what is left is about geostationary satellite. What is a geostationary satellite? What are its application? And there is a specific point in geostationary satellite because of their time period is equal to 24 hours. That is why these satellites always appear to be stationary. So as per the textbook will be a reference. You can slightly move far away from your textbook. I just only want you to present your geostationary satellites. You can question your other students also. Not necessary on Sunday. Whenever you have your moral education or your zero period, want to make only one student, boys, you need to speak up, right? After you hardly, this year is already over. One more year you will have. After that, you will go for your professional course, 4 years. Then when you go for your interviews, now it's all about what do they say is that even when you go and join your workforce, you need to present, right? Whatever your project work, you need to speak. That's very important, boys. So please take up your work. I don't want Abel. I don't want what's that? Siddharth, because these children are doing their work. I want others to take up. Fine, I'm not just wasting. I'll put the names. Two of you share and just, it's only your class you are presenting, boys. You have to be confident. All can do. It's not that nobody is having the capacity. Everyone are having your potential. Only thing is that even if it goes wrong, not at all an issue. It's a class. Others will help you out. Just two of you. I'm not singling out any one student. Two of you, we can just put it. Okay. Right. I'll just finish off gravitational potential. So what we started with this, right? You have a body M which creates a gravitational field. In this gravitational field, say at a point P, if I want to find what is the gravitational potential energy. If a body is, say, if a body of smaller mass m is lying at point P in the gravitational field produced by the massive one, then you know what is the work you do in bringing this body from infinity to this point P. There is another one, what we call it as gravitational potential. Only thing is that in the previous case, you had a body of mass, say 5 kilograms, 10 kilograms, whatever it is, it was at infinity. Now you think this body which was at infinity is a unit mass. So the work you do in bringing a unit mass from infinity to the point P measures the potential at point P. That is the gravitational potential at point P. It is nothing but the work you do in bringing a body of not any mass. In the previous case, it was a body of any mass, might be 5, 10, whatever it is. Here it should be only unit mass.
Time's up.
Yeah. To point P. Who is that? Who was that? Kritya? Kritya?
No, not Kritya.
No, I know. I'm asking him. Who was it? Kritya? It was not Kritya. I know. I can identify his voice. Fine, boys. Just a statement. What do you have next period?
P.
Oh, for that only you are running. Okay, fine, boys. Anyway, this is what is about gravitational potential. The statement we can do it. So almost the theory part of this chapter is over. Only that I'm assigning geostationary satellite work to you, boys. Okay. P is your integral part, right?
Ma'am, we have to write V equal to work done by mass.
Yeah, yes. I'll just do that. Only one clipping is left behind, boys.
Oh, okay.
Thank you, boys. Can leave.
Thank you.
Thank you, boys.
Thank you, ma'am.
Thank you, boys. Just put a message.
Thank you, ma'am.
Put a message to Hitesh that I have just, because I was not able to